Okay, so on page 30, we're looking at Newton's universal law of gravitation. Good morning, Nick. We're moving totally away now from force analyses. Newton's universal law of gravitation is a law that we can use throughout the universe. That's why we call it the universal law of gravitation, to find gravitational forces acting on objects. And we will talk about that in more detail in a second, but I want to take you back to probably grade 8, and then we talk about this a lot in grade 10. If two quantities are proportional to one another, this is what we write. We write that little weird squiggly symbol, and we read that as y is proportional to x. That means something. Specifically, it means that if you were to plot a graph showing the relationship between the two variables, you would have a line that goes through the origin, and it would be a straight line. And you learn in math class that a straight line has a particular equation. And the equation of a straight line is, well, I'll write it down, but the actual letter and notation that we use is unimportant. The equation of this line in math is y equals mx, and I hope that rings a bell. It's actually mx plus b, but b is the y-intercept, and we can see that this graph goes through the origin. What we like to say in science is rather than slope, well, I mean, it is slope. It's very important that you understand that this constant is a slope. But in science class, and particularly in physics, I like to point out to you, since the line is straight, the slope is the same everywhere, which means we like to talk about that number as being constant. What's an example of something that follows this relationship? Well, I'm not feeling very creative this morning, and I do want to come up with an example that is for sure perfectly proportional. What we could have here is number of liters of gas that customers on a particular day put into their tank in a gas station, and this could be the cost in dollars to fill their tank. And the idea behind this being a straight line can be summarized by simply saying, if you were to have twice as many liters of gas that you're buying, you're going to pay twice as much. And the slope of the line has some physical meaning. If we were to find the slope of this line, and let's just say, I'm going to make up some numbers here that may not be reasonable at all, okay? And I'm going to say that this is 10 liters. And this is 70 liters. This is $35. And I just have to calculate something off screen. Give me a second. And this is 245 liters, $245. So obviously what's not reasonable about this is the price of gas is like crazy here. But this is maybe in the midst of a zombie apocalypse or something, and the economy is all out of control, and who knows what's going on. But if we find the slope here, the rise would be the difference between those two, $245 minus $35, which is $210 for the rise. The run would be the difference between 70 liters and 10 liters, which is 60 liters. So what would our slope be? Our slope was rise over run, which would be $210 divided by 60 liters. And if I've done my math right, that's 3.5. Am I right? Can you do a calculation for me here? Okay, so this, thank you, Liam. So the slope of this line is 3.5, but more important, it's dollars per liter. And the point I want to drive home is that when you have quantities in the real world that are proportional, the slope of this straight line has a real world meaning. That slope is telling us that it's $3.50 per liter. So the slope of the line that shows proportionality between two variables means something. Now, let's get back to your notes now. The universal law of gravitation is a physical law. It turns out it's a formula that describes how any two masses are attracted to one another. And that force of attraction between any two masses is called a force of gravity. So up until now, you have just been taught that the force of gravity is something that pulls you towards the Earth. But the fact of the matter is, the force of gravity is a force between you and the Earth. So you're standing on the Earth. This is obviously not drawn to scale. You're standing on the Earth, and there is a force pulling you towards the Earth, but there is also a force pulling the Earth towards you. And these two forces are equal. This is really Newton's third law of motion, that for every reaction, there's an action. For every equal force in one direction, there's an equal force in the other direction. So when you take your mass times g and get, I don't know, 500 newtons, the force of gravity acting on you is 500 newtons downward. The force of gravity acting on the Earth is 500 newtons upward. A force of gravity exists because, and we really don't know why this is the case yet. It's a little tiny hole in modern physics. The force of gravity exists because any two masses are attracted to one another. The coffee cup that I'm drinking tea out of right now experiences a force of attraction towards my head. It's a very, very tiny force of attraction, but any two masses are attracted to one another. And the universal law of gravitation relates the two masses that are attracted and the distance between them. I want you to notice that the distance that we use, the symbol that we use here in the universal gravitational world is r. We use r for distance. And I also want you to notice that it's a distance from the center of one object to the center of the other object. Now, Isaac Newton, this is the old fable-like story, sitting underneath the apple tree, starts to come up with ideas. He did come up with these ideas. They probably didn't flash into his brain because an apple hit him on the head. But one of the things that Isaac Newton hypothesized, which means predicted, is that the gravitational force is proportional to the product of the two masses. What does this mean? Well, going back to our gas example, things are proportional if it's a straight line. But I want you to notice something, and we can check this out now. I'm going to put 20 liters on here, and I want you to grab your calculator. And knowing now that it's $3.50 per liter, knowing that the cost of gas, which is the slope of the line, is $3.50 per liter, I would like you to calculate the cost for 20 liters. 70. Really simple math problem. That means that it's $70. Okay, so here's the idea behind a constant proportionality. If I double one of the variables, I go from 10 to 20 liters, the other variable doubles. It goes from 35 to 70. This is a very important way to look at a proportionality. If I were to take 10 liters and multiply it by 7, that would take me to 70 liters. What happens if you take $35 and multiply by 7? Well, check it out on your calculator. 35 times 7 will give you 245. I sure hope so. Excellent. What would you have to multiply 20 by to get to 70? Well, I think it happens to be 3.5. So to go from 20 to 70, you multiply by 3.5. To go from this to this, do we multiply by 3.5? 20 liters is $70, so let's multiply 70 by 3.5. Does it give us 245? It does. This is the idea behind a proportionality. So getting back to Newton's first proposition, which is this, what this is saying is if you have two masses that are experiencing a gravitational force of attraction, if you were to double one of the masses, you would get twice the force of attraction. If you were to take one of the masses and multiply it by 10, change the mass, swap it out for something that has 10 times the mass, you would get 10 times the gravitational force. And by the way, and you don't need to write this down because we will have examples later, if I were to take this mass and double it, and this mass and triple it, then I would get 6 times the gravitational force. Okay, so that's the first proposition, and that's pretty easy to understand. The second proposition is more nuanced. It's more subtle and complicated. What we say here, and I'm actually going to write this down so that you can see the words. I think it's important that you see the words here. This is saying the magnitude of the gravitational force is directly proportional to the product of the two masses. That's what that statement is saying. Directly proportional means as one changes, the other changes in the same way. So if you use twice the mass, you get twice the force. What the second statement is saying is that this is what Isaac Newton believes, okay? Is that the force of gravity is, the word we use is inversely. I wish we used the word is reciprocally, but that's okay. Is inversely proportional to the square of the distance. And I want to just go through a very quick example numerically of what that means. Let's say that we had a gravitational force between M1 and M2 when at 2 meters apart is equal to 12 newtons. Don't worry about whether the numbers are reasonable or not. So what I'm saying is I take two masses, whatever they are, I put them 2 meters apart, and there's a force of attraction between them of 12 newtons. If that's the case, then the force of gravity, I'm going to change this to 3 meters. Then the force of gravity between the same masses (6 meters apart) is, now, I don't expect anybody to get this answer. I expect some people to get an answer with a little bit of help from me that will be wrong but along the right track. Inversely proportional means that as one of the quantities goes up, the other quantity goes down. And stop and think about this before you try any calculations here. Doesn't it make sense that the force of gravity would be smaller if the objects were further apart? Whatever is connecting them, and we really, honestly, we really don't understand this. Not us. Physics really doesn't understand what's actually going on here. There's a hypothesis, but it hasn't been proven yet. Why is it that the moon of Jupiter is attracted to Jupiter and Jupiter is attracted to a moon around it? We don't really know, but they are attracted. Whatever is connecting these two things, I think it's reasonable to say the closer they are together, the greater the effect will be. So, going to my quick off-the-cuff illustration here, if we go from 3 meters to 6 meters, we've doubled the distance. That means the gravitational force should be less. Does anybody have a guess as to what you believe the gravitational force will be? Liam says 3. Cole says 6. Good morning, Hunter. So we've got two answers, and I will tell you right now, one of the answers is what 99.999% of the people will say at this point. And it is the wrong answer, unfortunately. One of the answers is in fact correct, and it is 3 newtons. The answer is going to be 3 newtons. And I have a feeling maybe some of you suspected it would be 3 newtons. But because I didn't instill a lot of confidence in you when I said nobody's going to get this, it's quite difficult. The idea is that there's an r squared here. So if you think about it, the force of gravity is proportional to the reciprocal of r times the reciprocal of r. So whatever happens to r, the opposite happens to the force. If I go from 3 meters to 6 meters, then I've doubled r, which means the force of gravity is going to be cut in half. But it gets cut in half twice. We divide by 2 squared in order to get that new force. And that's how we can go from 12 newtons to 3 newtons. We'll get some official practice with this later, but I wanted to just give you an idea of what that means. What this second statement means, everybody, is the following. Whatever happens to the distance, the opposite of the square happens to the force. So that's Newton's hypothesis. Now it turns out that if you have the force being proportional to the product of the masses and the force being proportional to the reciprocal of r, that mathematically we can say the force, according to Isaac Newton, of gravity between two masses a distance apart will be proportional to m1, m2 over r squared. This is Newton's hypothesis. Well, that must mean that Fg is equal to some constant times that m1, m2 over r squared. The reason for that is because when you have a proportionality, y is proportional to x, that means y is equal to some number times x. So if Isaac Newton is saying y is proportional to x, then that means that y is equal to some constant times x. And the constant, of course, would be the slope of the line if you were to plot these quantities. All right, so a guy by the name of Cavendish verified this. Think about what this means. Think about what this means. And we'll talk in Physics 30 about the exact details. What it means is that if Isaac Newton is right, if these two quantities are proportional, if you plot force of gravity on the vertical axis and m1 times m2 over r squared on the horizontal axis, you will get a straight line. This is what Cavendish did. It's really hard to visualize, but what he did was he hung a lead ball from a wire, and he hung another lead ball from a wire, and he put the two lead balls close to each other, and believe it or not, this is an oversimplification. When you do that, and again, this is a vast oversimplification, when you hang those two spheres close to each other, they pull together. That's not exactly how he did it, but it's easier for me to explain this way. And when you see this done, if you take physics in university, you actually do Cavendish's experiment. It's spooky. You put these two things together and all of a sudden they start moving towards each other, just very, very lightly. The angles that they are deflected are not much. So he was able to measure the force by determining how much they are pulled towards each other. And of course, measuring m and r is pretty simple. And the bottom line is when he plotted them, he got a straight line. And that verifies Newton's hypothesis. This is maybe the most important thing so far. This graph that Cavendish comes up with says Newton is right. And by the way, a lot of what I'm doing is not in your notes, and there is absolutely no reason for you to write it down. Cavendish proved Newton right. Much like when you did your uniform motion lab, your hypothesis was that the distance should be proportional to the time. When you got a straight line, your hypothesis was verified. But more to the point here, if Newton is right, then we have an equation. And that constant in the equation is going to be the slope of the line. I really want to stress that we go from having a proportionality, which is really not that useful in science, to an equation which is very useful. Well, Cavendish determined the slope of the line. He did this experiment many times over many years, and when he picked a point on the line and a point on the line, and he drew a triangle, this would be the rise, and it would be measured in newtons because it's a force. This would be the run, and it's measured in kilograms squared over meters squared. Because if you look at what you're plotting mass times mass over r squared. So when you take the units of newtons divided by this, let's just see what we get. Newtons divided by kilograms squared per meter squared. You learn in probably grade 8 math, maybe even earlier, when you divide by a fraction, you multiply by the reciprocal. And that's why we have this set of units for the slope. The number itself turns out to be very small. And in Physics 30, we talk about the significance of that. Gravity, it turns out, is the weakest of all of the forces in the universe. And it's because this number is really small. What this 6.67 times 10 to the negative 11 means is 0.00000000667. So I've taken the decimal place, which was here, and I've moved it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I had the number of decimals wrong. I guess I need one more. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There we go. So it's a very, very tiny number. But here's the point. And I used to teach this years and years ago when I first started teaching by just giving you the equation. I think the science behind it is important, especially in preparing you for Physics 30. This value is the constant of proportionality, which means now we go from Newton's hypothesis to an equation. Now we have something we can use. This number is called capital G. Don't confuse capital G with lowercase g, which is 9.81 meters per second squared. I want to ask you guys a question here. Is g, little g that you're looking at, is it always 9.81 meters per second squared? No, definitely not, right? It depends on how far away you are from the Earth. It depends on what planet you're on. It depends on a lot of factors. This is what we would call a local constant because it depends on the location. This is called a universal constant. Look at this word. This is a universal constant. Everything that we, being the physics community, believe to be true tells us that if you were to do Cavendish's experiment on the moon, and they actually have done it in orbit, by the way, if you were to do it on the moon or a different planet or a different location on Earth, you always get this number. So now we have this equation. We go from Newton's hypothesis to Cavendish's proof to an actual equation that we can use to calculate the force of gravity between two objects. And we'll learn more about satellites and planetary motion later, but this equation allowed scientists to finally know the mass of the Earth. Prior to Cavendish's experiment, they didn't know the mass of the Earth. Now it's very easy to find it. What you do is you measure the weight of an object. You hang the object from a spring scale and measure the weight. The ancient Mesopotamians knew the radius of the Earth. We now know this, and you know the mass of the object you're hanging from the spring scale, so you can calculate the mass of the Earth. Very, very valuable equation. So what we're going to do is use that equation today, but I want to familiarize you with your formula sheet. Under dynamics, you will see the universal law of gravitation. We, honestly, everybody, very rarely do we ever include direction, which is why the absolute value signs are there. So the force of gravity between two masses is g m1 m2 over r squared. You can see the gravitational constant is in the constant section of your formula sheet as well. And let's get to it. Determine the gravitational force of attraction between a person and the Earth using Newton's universal law of gravitation. So what we're going to do is write out that the force of gravity on the person will be equal to g times the mass of the person times the mass of the Earth divided by the distance between them squared. But this is really, really important, what I'm about to say. When I'm standing on the Earth, I know that the distance between me and the Earth is 0. However, in the formula, it's the distance between the centers of the objects. If I go back and look at the original diagram that started this whole discussion, the original diagram is here. And I made a point of telling you that r is the distance from the center of one object to the center of the other object. So when we start to look at a person standing on the Earth, When we start to look at a person standing on the earth, this is the earth, here's the person. What is the distance between them? Well, the distance between them is the line connecting the center of the earth to the center of the person. But what that is the radius of the earth. So what we're going to put in the bottom here is the radius of the earth, and we need to square it. And now we're going to put in all of the numbers. And it's going to be a little clunky because we have all of these units. After a while, you'll be able to do this calculation without even writing it down. Capital G is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. The mass of the person is 65 kilograms. The mass of the earth is, well, we can look at the formula sheet. On the formula sheet, the mass of the earth is also given, as well as the radius of the earth. So the mass of the earth is 5.97 times 10 to the 24 kilograms. I'm pretty sure I remember what the radius of the earth is, but I'll ask for verification from some of you. It's 6.37 times 10 to the 6 meters. Okay. Look at how I wrote that. You know me, I'm picky. If we're going to do things, we're going to do things right. You cannot write this. That is wrong. This is wrong. Because what you're telling me is it's 6.37 times 10 to the 6 square meters. And we want to square the whole thing, not just the units. So now we're going to calculate this, and listen very carefully, because I know from experience some of you are going to make this more complicated than it needs to be. There is no reason to use brackets anywhere here. When we enter 6.67, I can see I've got a little typo there. Well, I wrote it, so it's a little righto. When we enter 6.67 times 10 to the negative 11, you do it this way. We go 6.67, and then you use the EE function on your calculator. The EE function is the second function of the comma key, which is above where my cursor is sitting right now on the 7 key. So I hit second and then that comma key, and then I enter negative 11. You do not put brackets around that whole thing. I've seen people put brackets and brackets and brackets. You don't need to do that. Times the mass of the person, times the mass of the earth, which is 5.97, multiplied by 10 to the 24, divided by 6.37 multiplied by 10 to the 6 squared. This is exactly how you enter it. You do not need to put brackets. Always when you have a complicated calculation, double check to see that you've entered everything correctly, and I have. So what we end up with is 638 newtons. So what we have found here, everybody, is the force of gravity between this person and the earth. In other words, everybody, we found their weight. But we have learned that you could find weight using this formula. So let's calculate the person's weight using that highlighted formula and see how close we get to what we just calculated. This is a simpler calculation, of course. We can take 65 kilograms times 9.81 meters per second squared. And we get 637.65. We do not get the exact same answer. And the reason is, when we use 9.81, we're using the local value of the acceleration due to gravity. What this answer at the bottom represents is an average throughout the whole Earth. I hope you know the Earth is not a perfect sphere. So the radius of the Earth in Wetaskiwin is different than the radius of the Earth in Bali, and it's different than the radius of the Earth in Mexico City. So you're going to get slightly different answers. Does anybody have any questions with that first example? All right, let's run through the second example now. Gravitational force of attraction between two masses is 4, and there's that mu symbol. Well, what mu means in this context is a metric prefix. If you take a look at your formula sheet, please. On your formula sheet, I believe on the same side as the constants, is this table. And mu in the metric prefix system means 10 to the negative 6. So we just have to get over it. Mu can mean coefficient of friction, or in a different context, mu can mean 10 to the negative 6. Just like kilo means 10 to the 3. You know, like I said, you have to get over it. If you walked into class tomorrow and I said, everybody write down what m means, my goodness, there's all kinds of answers you could put. You could say it means mass. You could say it means meter. You could say it means milli. There's at least one other thing that's escaping me, but it's all contextual. So this is 4.0 multiplied by 10 to the negative 6 newtons. So the mass of each object is doubled. Well, the force of gravity is proportional to the masses. So if I double a mass, the force doubles. If I double both of them, I'm going to double the force and double the force. So we're going to have 4 times 10 to the negative 6 newtons. We're going to have to double it because we're doubling one of the masses. We're going to have to double it again because we're doubling the other mass. And what we end up getting is this number. So when I enter 4 times 10 to the negative 6 newtons, I go 4, hit my EE button and go negative 6, multiplied by 2, multiplied by 2. So you get 1.6 times 10 to the negative 5 newtons. B, the distance between the two masses is doubled. So remember that the gravitational force is inversely proportional to the square of the distance. That means the gravitational force is proportional to the reciprocal of r times the reciprocal of r. So if I double each of those r's, the result is I'm going to cut the force in half, and I'm going to cut it in half again. Which means that the new gravitational force will be 4 times 10 to the negative 6 newtons divided by 2 squared. So for B, you're going to divide by 2 squared. And by the way here, everybody, what I'm doing in this question would never be a written response kind of thing. I don't think there's really, after a while, much work to show. In A, well, you double the mass and you double the mass, so let's multiply by 2 and by 2. You're welcome. You're welcome, Ben. In B, we double the distance, and since the distance is on the bottom of the formula, we have to divide by that 2, but we have to divide by it squared because there's r squared there. For C, if I were to triple the distance, then I would take the original force and I would divide by 3 squared. So tripling the distance will result in 1/9 of the actual force, which I believe gives you 4.4 times 10 to the negative 7 newtons, but it is, okay. Any questions with example 2? All right, let's take a look at number 3. Mount Logan in the Yukon is 5,959 meters above sea level, and it's the highest mountain peak in Canada. What's the difference in the weight of a person at the top of the mountain as compared to the base? Let me know when you're ready, Miriam. For B, okay, you better, we'll try to. So let me know when you're done with B, please. Are you okay with C, Miriam? You sure? Okay. And again, don't be afraid to do that. Let me know if I need to go back because we're all on different internet connections. You know, some of you are getting this later than other people. It's kind of like having a conversation with somebody on the moon. And it's one of the reasons, by the way, why, you know, it's taking us longer sometimes to get through this material than it would normally in the classroom. So what we need to do here is understand that when a person is on Mount Logan, so here is the Earth, and here is Mount Logan. I realize this is not to scale. That when they are on the peak of Mount Logan, the distance that we would use for r in Newton's universal law of gravitation is the distance from the center of the Earth to where that person is. But when a person is standing at the base of Mount Logan, the distance will be from the center of the Earth to the person, which means when they're at the bottom of the mountain, they are closer to the Earth mathematically, and what that means is they will weigh less. So I'm going to try to set this up and give you a few minutes to do the calculations. The distance between the center of the Earth and the person when they're at the base is the radius of the Earth. It's 6.37 multiplied by 10 to the 6 meters. The distance when they are at the peak of Mount Logan, this distance is more than the radius of the Earth. That distance will be 6.37 multiplied by 10 to the 6 meters plus the 59 meters. It will be more. So now we can do the calculations using Newton's universal law of gravitation. At the top, the weight of the person will be g. and I'm going to leave the units out of it this time. There's g multiplied by the mass of the person, which is 55 kilograms, multiplied by the mass of the Earth, because that's the planet they are on, which is 5.97 times 10 to the 24. And then we're going to divide by, when they are at the top, 6.37 times 10 to the 6 plus 59 quantity squared. And if you want, you can certainly add these two numbers together first and get a new number, but I'm going to show you that it's not necessary. Let's calculate that. So there is my g, 6.67 times 10 to the negative 11 times 55 times the mass of the Earth from your formula sheet. Is that right? 5.97 times 10 to the 24? Okay. Divided by, in brackets. Now we do need a set of brackets this time because these two numbers need to be added together before they're squared. 6.37 times 10 to the 6 plus 59. Double check. There's my, I'm just looking at my calculator screen to make sure everything is in correctly and it looks okay, except if I would have hit enter, I forgot to square, which is a very, very common mistake. So what I get is 539 newtons, 538.7. When they are at the bottom of Mount Logan, so at the base, Fg will be g. Now I'm going to do something here. G is a universal constant. My goodness, do I have to write down 6.67 times 10 to the negative 11 every time I use it? Let's just write capital G times the mass of the person times the mass of the Earth over the distance between them squared, which would just be the radius of the Earth. By the way, there will come a time where you should be able to do these calculations without even writing anything down. If I give you a multiple choice question, it's a matter of putting those numbers into the formula, which is in front of you, and your writing it down could be considered something as simple as writing it down in your calculator. I'm not trying to say don't show your work if you have to. Times 55. Actually, you know what? I'm just going to do this. Get rid of this. I don't need the brackets here, but it's just the way I edited it. And what I get is 539.7. So the person weighs approximately 1 Newton more at the base, or they weigh approximately 1 Newton less at the peak. So you want to lose weight, go to the top of a mountain. And by the way, you'll burn a lot of calories on the way, so you will truly lose weight in what you think of being weight loss. Any questions with number 3? Does anybody need me to hang around on this page for a few more seconds to copy anything down? Please let me know if you do. We've been going at it for about an hour and 15 minutes. About 45 minutes has been on this new lesson. We'll just take a pause here and please give me some feedback. Too fast, too slow, just right. And I apologize, Ben and Maram. I didn't have my chat open until now, so I didn't see some of those messages. Might have been late coming to me. So we're okay, it looks like. All right, we have one more example to do. Object A exerts a gravitational force of 1.3 times 10 to the negative 10 newtons on object B. So you really don't need to know what I'm about to say to answer this question, but I want to make sure you understand it. You have two objects, A and B. It says object A exerts a gravitational force of 1.3 times 10 to the negative 10 newtons on B, but that means that object B exerts the same gravitational force on object A. I don't want anything to lead you to believe that if a gravitational force is a certain amount, that half of it goes to each object. The gravitational force is whatever the gravitational force is. So what happens here? We double the distance. We take one of the masses and we multiply by 6. We take the other mass and we multiply by a half. What's the new force? So I don't believe that this is a matter of, showing a lot of work. I'm just going to write down the formula. But I'm going to write it this way. Instead of having over r squared, I'm going to write over r over r. So think of this as like a seesaw, a teeter-totter that's perfectly balanced. If I were to double the mass of one of the objects, then that teeter-totter would no longer be balanced. I would have to double the other side to make it balanced. So this is the basic idea, that I'm going to multiply. I'm going to squeeze this in. It may not look good. I'm going to multiply this mass by 6. I'm going to multiply this mass by a half. I'm going to multiply this r by 2 and this r by 2. I better rewrite that. What we end up with is the new gravitational force is g times 6m times 1/2 m over 2r, 2r. So what I'm doing is multiplying the top of that expression by 6, and I'm multiplying the top by a half, and I'm dividing the whole expression by 2, and I'm dividing the whole expression by 2, and that means that all of those things are going to happen to the force. There's really no work to be shown here, and I would never want an explanation in words. The force was 1.3 times 10 to the negative 10 newtons. We have to multiply that by 6 because multiplying a mass by 6 increases the force by a factor of 6. We have to multiply that by a half because multiplying a mass by a half reduces the force to 1/2. And we have to divide by 2 because doubling the distance cuts the force in half, but we have to divide by 2 squared. And there will come a time, everybody, where you will just read this question and say, well, okay, let's see, 1.3 multiplied by 10 to the negative 10 is the force. So what do? Oh, we multiply a mass by 6. We multiply a mass by a half, which is 0.5. And we multiply, this is why it's an inverse proportionality. We're multiplying the distance by something which results in the force being divided. But what we multiply the distance by, the force gets divided by that number squared because of the inverse square law. Lots of ways to think about this, but I get 9.8 times 10 to the negative 11 newtons. Just to double check here with you people, anybody else get that? Okay, I'm seeing a couple thumbs up, that's good. So you can see why, 9.8 times 10 to the negative 11 newtons. 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 9.8 times 10 I'm only doing one lesson today, obviously. If we were still in the classroom where we would put 2 lessons in, I could have gotten through this maybe a little quicker, but it really would have been pushing it even in the classroom. If we were doing this in the classroom, I certainly would not have spent the first half hour explaining the previous few days. What are we dealing with here? We're dealing with assignment B, which is on page 33 of your handout. There are just boatloads of problems here you can try. Please try to remember that when you're finding the force due to gravity for an object above the surface of the Earth, you need to add the radius of the Earth to how far above the surface of the Earth they are to get R. And incidentally, that distance above is called altitude. So for example, when you take a look at question 4, the altitude of the spacecraft needs to be added to the radius of the Earth to get the distance. So I will zip my trap here and let you guys get to work. You have about 35 minutes left before the class officially ends, but as usual, I'm here till 11:30. Please let me know if I can help you in any way.